What I'm going to present today is an experimental talk, maybe even more so, it's an applied talk. However, if you're a theorist, don't be put off because it's something that you can do from the comfort of your desk if you like. So what I'm going to talk about is something which turned out to be fairly simple after 6 months of work. And it's how do you make a random number generator where the numbers are of quantum origin, hopefully, and which works on a mobile phone. Well, why do we want to do this? Why are we motivated by this? Well, random numbers are very important because for all security, it's been known for a long time that your algorithm has to be, like the security of your algorithm has to rely on your key. So if all of the, so this guy here, Auguste Kerch, I don't know how to pronounce that. Anyone Dutch in the audience? Kerkhoff? Well, Auguste Kerkhoff. Well, he came up with this principle that all of the security of the cipher has to reside in the key. So the problem is that if you can guess the key, then you can crack any system. So here I have chosen a set of systems which have been cracked by attacking the random number generator. So, for example, when I was at my university, the first time I encountered this is in 2008, when one of my servers suddenly stopped working. So I went to the server room because I couldn't connect to it, and the Linux on it had decided to stop all connections because all of the keys were predictable. And so that's a really drastic, so for an update to really stop all connections to a server is a drastic measure, and that's Debian, so that's one of the biggest Linux distributions. So luckily, it seems like, some white hat hackers had found that first and decided to go through with some updates. So then some other hacks have been done, for example, not only on server security, but also on copyright infringement. So like PlayStation. So there are billions of dollars invested in this, but the random number generator was hacked, and everyone can copy now games of the PlayStation 3 if they like to do so. It's not just that. So also mobile. So Android also suffers from that, and also financial software has been hacked that way on these Bitcoin wallets, and everyone expects that mobile phones will be used more and more for financial transactions, so that could be a problem if you can hack them. Another problem is, of course, well, Windows, of course, has been hacked. The random number generator has been hacked. And also, very recently, it has been shown that a few % of keys around the world are actually the same. This is this last reference here. So this is a huge problem. So what can we do next? Well, here I put a list of random number generators which are commercial now, and which can, from the worst one to probably the best one, I hope. So the worst one is the software random number generator, which, of course, computers are deterministic, so unless you have a good random seed, you cannot generate a good random number. So then we asked what people use. So they might use a microphone in your mobile phone to try and collect some random data. But of course, you can put some ambient noise, which will seem random, but it isn't. People use PLL loop. So for what that is you put a very fast oscillator, a very slow oscillator, and you sample the fast one with the slow one. And if the design of the system was bad enough, well, then when you sample the slow oscillator, the fast oscillator, it will have a random value. So that's actually how this is implemented in Intel and VIA chips and some other ARM chips in mobile phones now. So there's no actual proof that that's random at all. Another way of doing it, which is slightly more secure, so which is used by companies which want a bit more security, is using the shot noise in diodes. So that's quite a slow process. Is more complicated than the above ones. However, it's a quantum process, and it works fairly well, but it's very sensitive again. maybe the best system that's available nowadays is this idée quantique quantum random number generator. So that's, just to show you what it looks like now, is about this size. And it's fairly small, it's fairly cheap, but I'm going to argue that it's massively too expensive and massively too big, especially if you want to put it in a mobile phone. So how does that work? Well, the principle is that you have a photon. It splits into two modes. If it goes one way, you say it got a 0. If it goes the other way, you get a 1. And because you say, OK, it was in a superposition before that, then that's quantum. So then the idea came, OK, what if we use something which is included in everyday devices, such as a camera, and we do something similar. So we have, like, instead of 2 pixels, we have many pixels, and the light will be in a superposition of being on all those pixels, and you get certain statistics from that light, and this will be Poisson statistics. You can calculate exactly the minimum entropy of your distribution, and then you have some randomness that you can use later. So just as a side note, I always get asked, OK, like, that seems like a neat little trick, so how did the idea come? And the thing is, well, the idea came because at the University of Geneva, we do like some fundamental research and to try and understand what a macroscopic quantum state might be. And to understand that, you need to measure a small amount of photons with very high accuracy. So you need to have a photon number resolving detector, which is very linear and which works well. So we tried a whole set of detectors, and it turned out that the detectors in the mobile phones are actually the best ones. So they're excellent. Why are they so good? Well, they're good because you have the very low noise. They have only 1 electron of noise. Why is that? Well, this is what the detector might look like. It's very small to put a lot of pixels in a very small area. So light goes through a little lens, it goes on a diode, and then the amplifier is like a macrometer. So the charges, whatever charge gets absorbed by the diode, it can't get lost. It always gets amplified. So that's really the trick why these small telephone detectors work very, very well. And also, it can, because it's a linear diode, the detector has very high linearity. So, OK, so we tested with 2 different systems. One system is a commercial astronomy camera, which we have very good control, and which we understand very well, and we can test our theory from. And the other one is that mobile phone. So the noise on this is slightly higher, 10 electrons. The noise on this is 3 electrons. So that's photoelectrons. So that's equivalent to 3. The noise of 10 absorbed photons, the noise of 3 absorbed photons. OK, so how does that detector work? You have a light source. Then, of course, it's not perfect. So there are some perfect CCD detectors or CMOS detectors, but it hasn't got unit efficiency. So you model that with a loss, a beam splitter, and dump. Then you have a perfect detector, so where a photon gets converted into an electron. The electron, so this charge then gets converted into a voltage, and then the voltage gets digitized from the analog voltage to a digital number, the output. So typically, every absorbed photon will result in increasing a counter by a factor of 2. So that is so that you don't have a number you don't have a number of electrons that you cannot represent. So this is what you get experimentally. You get so this is theory. The Poisson distribution is purely from theory. It's not a fit. It's just like measuring how much light we put on the detector. What do you expect to see? And this is the green histogram is what we actually measure. So actually, interestingly, so this is with the astronomy camera, this is with the Nokia camera, and you can notice a little bit of discrepancy on these graphs. It's a bit less perfect than this. So why is that? It's because actually, as we were saying earlier, the analog to digital converter has 2 values for representing each electron. So of course, the odd numbers are slightly less likely than the even numbers because the noise is so low that you always measure kind of an integer value of electrons here. But this doesn't really matter. As soon as you have enough values to represent your data, you're fine. So with these two cameras which we tried, which are nothing special really, you get, with the astronomy one, you have a noise of 10. You can put up to 2 × 10⁴ photons on it. We put nearly that number. And you get some entropy of 8.3 bits per pixel. And because that's encoded over 16 bits, you get about half a random bit per bit of output. And these are the values for the mobile phone. You still get about a bit more than half a random bit per bit of output. And you get 10 bits per pixel. So now you say, OK, so this is not quite perfect. Now, is that a problem? Because like, we do have a little bit of noise on the detector, which is not of quantum origin, which is maybe like some readout noise, which is like electrical. So is that a problem? So OK. So how do we think of that? Well, say I'm Alice, and Vadim is Eve. And say I want to, what data do I have access? I have access only to the convolution of my quantum noise, represented by this curve, and the technical noise, which is represented by this distribution or any other distribution. So I have access only to the convolution of both, which is any function, really. If I have, now, what does Eve have access to? So what's the entropy of this system from her point of view? Well, because she knows the technical noise, so she knows exactly what the technical noise was, she can subtract it from this convolution. And then she can recover just the quantum noise. But she cannot do any better. She cannot guess what number I measured to better than this distribution here. So that means that if when I design my randomness extractor, I use just this quantum noise as to calculate how much entropy I should have, then the classical noise does not actually play a role. So we did use some low noise detectors, but you could use some detectors with higher noise if you wanted to. It shouldn't be a problem. So this is actually to generate more entropy, what you want to do is to have a larger and larger amount photon number per pixel. So you generate for each factor of 10 in photon number, you generate about 2 bits of entropy. And typical detectors have between 1,000 and 100,000 photon charge capacity. So you can generate, say, between 6 and 10 bits of entropy per pixel. So other things that you have to be careful of? Yes, there are. So one thing is you have to be very careful that your detector does not saturate. Because if you put too much light on your detector, then, well, it will always give you the same number out. So like, say, the maximum digital value that it can put is like 1,000. If I put too much light on it, it will always say 1,000. And then there's no entropy in that. So what's plotted here is the variance divided by the mean. And for a Poisson distribution, it should always be 1. If I get less than that, it means that I have some saturation or some nonlinearity. And if I get more than that, it means that my noise is much larger than the quantum noise. So you have to set your detector, you have to put an amount of light, which will ensure that the number of photons that you have is kind of in the middle here. It's not too low and it's not too high. You want to operate in the linear regime of your detector. So once you know how many photons you have, you can use a randomness extractor. OK, so here I put the matrices the other way around for the multiplication, otherwise it didn't fit. So you have a matrix with your random data, which actually has 2,000 values in reality. And you have another matrix which has some random data, but which could always be the same. It could also be public. You don't have to change this matrix ever. Like there's one of these matrices which has been made by Renato Renner on the website of Idée Quantique. You can download it and use that if you like. So this extractor what this extractor does is that it condenses all the entropy here by making this matrix multiplication, all the entropy in your input data into a smaller number of output bits. And the calculations from Troyer, Renner, and Daniela Frauschiger can tell you exactly how many trials you need to do before you can notice a deviation from a perfectly random bit string in your output data. And that turns out to be, from theory, that is something very, very high of the order of 10 to 96. So in this paper, it also tells you a number of ages of the universe. So that is, if everyone on Earth used at a gigabits per second, is like 10 to the 60 times the age of the universe or something ridiculous before you could distinguish this string from a perfectly random one. So we also did a few randomness tests for what they're worth. So these are the die-harder tests. There are many, many tests. We only represented a few. I think most random number generators which are decent do pass all these tests. So there's nothing special, but it's kind of reassuring that it does. Also, however, what is more interesting is to look at things such as autocorrelation. So it's for looking for errors that you know that your detector might have. So some electrons, for say, from one pixel could go to the next pixel, or some electron, or the efficiency of your detector of one pixel could be higher than of the next pixel. So that is the case. So we checked that all those values are, so that there is no, so that all the correlation values are not a problem for this. So for example, one pixel might be dead, but of course the extractor would solve that easily. So another question is, what kind of speeds do we get with this system? Well, the limit is not the transfer speed. Actually, the sensor, of course, is made to do video nowadays, so it can do 30 frames per second per 8 megapixels, 3 bits per pixel, so that's 720 megabits. And that's like a $1 device. If you spend a little bit more money, like $3, then you can go above a gigabit per second. The clock, so of course, the more, if you want to do those speeds, the more expensive component is an FPGA or CPU that will do the extraction fast enough. So we did it in software in a very naive implementation, and we got about the order of, say, between 1 and 10 megabits, depending on where we ran the software. On the FPGA, collaboration between the University of Geneva and ID Quantique, we got 1.25 gigabits per second extraction speed. On the mobile phone also, it's like you can see here, what you're limited by is the memory, because you don't have too much memory on the mobile phone. That can be a problem, because when you're measuring your entropy, then it's, yeah, you don't have enough statistics. And you can see a little bit of that. So you have a bit, like some tests, they haven't failed. It's like to fail, they have to go below this, but the result is slightly weaker than on the other camera. So do you really have to use a calibrated source, which we had in the lab, you know, with a LED and a fiber and power meter, which was very well calibrated? Or could you just use any source? Well, actually, in principle, any source is good enough. As soon as, because you do have a little bit of loss in your detector. So if you could say, OK, I just measure what goes on here, and if it hasn't gone on here, it's been absorbed by the detector, and I'm not giving that to Eve, so that's still fine. You could use anything. But the complication is that then for every pixel, you would have to design an extractor specifically. So say if you took a picture of a cow, then for the dark bits in the cow, you would have to have an extractor with much more compression, because there's less photons there, than for the white bits of the cow. So it's a bit more complicated in practice, but it could be done. Of course, yeah. So of course, one thing which the referees asked in the paper is to check that the source that we used had the distribution that we thought it had, which we did with a single photon detector. And again, this is not a fit, is a calculated curve. And you can see that the measurement points for nearly exactly on that curve. So any source is fine, actually, if you want to do the software. Final advantage of this system is that you can integrate it on a chip very easily. So because it's all CMOS, so CMOS is a technology that people use to make silicon chips, like well, any silicon chip nowadays uses CMOS technology, not just processors, but also transmitters. So you have little LEDs and lasers in CMOS. You can also have the sensors that's in CMOS, and the processing can be in CMOS. And you can also do some waveguides, if you like, in CMOS to transfer from a light source your photons all the way to a sensor pixel. So this could all be integrated in some like square microns of silicon, giving you access to the random numbers directly. So this would be good to have everything in a small space, I mean, to make it cheaper, but also for security. So to conclude, yeah, we saw that with a cheap image sensor, you can do some experiments at the quantum level. Also, these can be used to do a quantum random number generator. One thing which would I emphasize is that, of course, we are experimentalists, and probably there's still some work to be done in terms of like what do we really mean by a quantum random number generator, how do we calculate that, how do we test that, and so on. So like I think that's something which we should look at in the future. Well, I thank you for your attention, and also this work was done by myself, Anthony Martin, Hugo, and Nicolas. And also I'd like to bring your attention that if you're interested in this kind of things, there's a ID Quantique Winter School happening in January, and you're welcome to participate. Thanks.
How can you be sure that someone's not just pointing a modulated light source at your detector?
Well, the advantage, say, if you're doing a random number generator with respect to all the cryptography systems, is that with random number generators, you usually have them in an isolated package. So, for example, this is also part of how you get something certified as being a good random number generator. You see, like, this has a metal package. Of course, if you have something which is just a few microns square of silicon, then you can really seal it very well from the environment. So that's how you would be sure. And of course, like with light, is harder for someone to put some light in here or to generate some light in here than it is to induce some electromagnetic wave or some radio wave inside the thing. So that's also an advantage, say, of having an optical system with respect to just normal diode, which will also generate a bit of shot noise.
Thank you.
So you can use the diehard to verify the randomness. So I'm wondering how you verify the really quantum randomness instead of classical randomness.
So I wouldn't say that the diehard would verify the randomness. So the diehard test, it verifies that you haven't got some trivial thing wrong, or that so it verifies more the distribution than the actual randomness of your system. To know whether it's quantum or not, I think it depends on your definition. So for now, our definition is that we say, okay, it's shot noise. We consider that to be of quantum origin. However, I think that there should be some work being done in the near future, also in collaboration with Zurich, which would at defining what do we actually mean by a quantum random number generator. Like we showed in the beginning, probably to be strict, you should have a single mode, split it in two modes, and measure that. But it's work to be done.
How can you be sure that you don't have correlations first in position between the adjacent pixels and also in time? Because I mean, you have you have only 30 pictures per second, but still there could be some kind of correlation between the data. Absolutely.
So you could. The thing is, you can have some correlations. For example, one pixel might have a slightly higher efficiency than another. That's absolutely possible. However, one pixel might be completely dead. However, these correlations are not a problem, because if you're quite confident on the mean number of photons on your pixel, then those correlations will never be beyond the quantum noise limit. So they will never be better than the shot noise.
Yes, you could have answered the previous question, but that will be, those irregularities will be smoothed out by the extractor.
Yeah, that's also.
But getting to this extractor, people worry sometimes that the operating systems and so on might have backdoors built in them, and you said you can get this, you can download this extractor from Idée Quantique. I don't think it's easy to build an extractor that has a bad backdoor built into it, but there's probably programs or directions for making your own extractors, which you can trust.
On the Idée Quantique website, you have not only the data, but you have like how that data was generated. So a lot of different random number generators were put together, and you could repeat that. But the problem is that you have to start off always with a random number generator that you do trust. So that's a general problem. You have to.
Which may just be a set of dice in your pocket.
It could.
Yeah. So the other question I was going to ask, which is related to this, is it seemed very attractive to do it with a commodity mobile phone, partly because if you do it that way, you can be pretty sure that the phone hasn't been hacked to give you fake random numbers if you just do it in software. But if you do it in hardware like you were proposing, then you have to trust who makes the hardware.
Absolutely. But again, so there's some work to be done in actually being able to test that the hardware does what you think it's doing.
Hi, just a little question. The picture you show with the autocorrelation is before or after applying the randomness extraction algorithm?
So that one was before, but we have done like, so this is only one picture, but we have actually tested the autocorrelation of like in a lot of different ways, so both temporal and spatial and so on. So you do have some correlations, like we did actually see that some pixels are more efficient than others. That is that's another field of study. It's used for fingerprinting of cameras and so on. But the correlations were never, of course, beyond the shot noise, of course.
And which is the sample size that you use for? So how many samples did you use to calculate this correlation?
10 gigabits. I think one gigabit. So you can see from how low it goes, to, what the sample size was. I think it was either 1 or 10 gigabits.
Okay, thank you.
I have a short question. Has any company contacted you?
Idée Quantique, yes.
Idée Quantique. Oh, so they are going in the mobile phone business?
No, but this is like it's an interesting aspect to study. There has been a lot of industrial interest actually on this, and like I don't know, but like really a lot of people have contacted me. Of course, to develop this kind of chip is something which takes a very large initial investment. So we'll see what happens.
I mean, it's a camera chip and an LED on top of it.
Yeah, but so one wafer of like the development of just one of the masks to make one silicon wafer is of the order of like on the hundreds of thousands of dollars. So, however, like once you got all the masks, you can make as many as you like.
In mask, you can just stack PCBs, one on top of each other. And
okay, so that's another thing. So if you want to make maybe, like medium size, medium numbers, you can stack the PCBs, yeah.